Hi everyone. So today let us discuss about the next part of oscillations. So already we have discussed three parts. This is oscillations part 4. Okay. Okay. Well, so let's start today's class. So in this class, I am going to discuss about the two very important derivations. One is time period of oscillation of a mass attached to a spring and time period of oscillation of a simple pendulum. Okay, first let us discuss about the derivation of expression for a time period of time period of oscillation of mass mass or load attached to a spring. Okay, so first here let us consider a vertical spring. Consider a vertical spring. So one end of the spring that is fixed to a rigid support and another end of the spring so that is fixed to a block. So this is of mass is m. Okay, m is mass of the block. So when the mass is slightly pulled down and then released, so it executes simple harmonic motion. Is it not? So when the body executes simple harmonic motion, if it moves to and fro repeatedly about a fixed point, under the action of restoring force, which is directly proportional to displacement of the body from the fixed point, and it is always directed towards the fixed point. Okay, so this is actually the fixed position. This is the equilibrium position, mean position. So what is this? The mean position. So at this position, displacement is 0. Okay, and these are the extreme positions of the mass M. So at extreme positions, so displacement is maximum. So this is positive amplitude. Let us consider this one as plus A and this one as minus A. This is plus A and this is minus A. Okay. So here we have to calculate. So what is the time taken by the block to complete 1, 2 and 1 fro? One complete to and fro motion. Okay. So when block is slightly pulled down and released, what happens? It executes simple harmonic motion, actually restoring force that is developed in the spring. Restoring force is developed in the spring. So by the definition of simple harmonic motion, definition of simple harmonic motion. So the force is directly proportional to displacement. So F is equal to minus ky. So here negative sign indicates sign indicates restoring force decreases the displacement, decreases the value of y. So and k is force constant, and that is also called the spring constant, force constant or spring constant. So, but according to the Newton's second law, so force is equal to mass into acceleration. So here alpha means acceleration of a particle execute simple harmonic motion. So alpha is acceleration. Alpha is here acceleration of mass m. Okay, acceleration of mass m execute simple harmonic motion. So what is the expression for alpha? Alpha mathematical expression minus omega square y. So y is the displacement of a particle execute simple harmonic motion. Alpha is the acceleration of a particle execute simple harmonic motion. So now this equation becomes F is equal to minus m omega square minus m omega square y. Okay, so call this as equation number 1 and call this as equation number 2. This is equation 1 and this one is equation number 2. Now compare these two equations, okay, 1 and 2. So from equations 1 and 2, so we can conclude that minus ky, that is equal to minus m omega square y. So here minus minus get cancels. So y is also cancels, right? So omega square value, that is k divided by m. So omega is equal to square root of k by m. So what is the expression for omega in terms of time period? That is 2 pi by t. Is it right? 2 pi by t is equal to root k by m. Then, so t is equal to 2 pi, t is equal to 2 pi divided by square root of k by m. So finally t is equal to 2 pi and this is shifted to the numerator. What happens? Root m divided by k. So this is the mathematical expression for time period of oscillation of a load attached to a spring, a mass attached to a spring. And this is a very, very, very important mathematical expression. So here m is mass of the block, k is the force constant, spring constant. And the frequency is F is equal to 1 divided by 2 pi root m by k. So this is the frequency of oscillations of mass attached to a spring. So this is time period and this one is the frequency. Okay, so this is actually 1 divided by 2 pi root k by m, root k by m, because the frequency is nothing but the reciprocal of time period. Okay, that means f is equal to here 1 divided by t is 2 pi root m by k. So 1 by 2 pi into root m by k. So that is shifted to the numerator. What happens? That is k by m. So this is the frequency of oscillation of modes attached to a spring. This is very important derivation. So the next one is the time period of oscillation of a simple pendulum. So this is the last topic in this chapter, derivation of expression for time period of oscillation, time period of oscillation of simple pendulum. And this derivation is also very, very important. Okay, first here, let us consider a metallic bob. Simple pendulum consists of a bob. Metallic bob is suspended from a long thread. Okay, so this is a metallic bob is suspended from long thread. Okay, so one end of the thread that is fixed to a rigid support S. So here SO, this is the equilibrium position. Okay, let us consider SO. SO is equilibrium position. So when the bob is displaced through a small angular displacement theta, the bob is displaced through a small angular displacement theta. So this is the displaced position of the bob. Okay. So SA is the displaced position. SA is displaced position of the bob. So theta, that is angle made by string of the simple pendulum with vertical. So this is vertical. So theta is angular displacement. So here at displaced position, how many forces acting on metallic bob? So that is very important. So in displaced position, forces acts on it. Okay, in displaced position, the displaced position forces acts on it. So one is the weight of metallic bob, which acts downwards. Is it right? Weight weight means force with which the body acts downwards. Weight which acts downwards. And number two, the second force, that is tension. Tension in the string. Tension in the string. So acts along the length. This is tension in the string along the length. Along the length. Okay. So here one is the weight of the bob, which acts vertically downwards. One force acting on the metallic bob at displaced position, and one more force acting on this bob, that is tension in the string, and that is acts along the length of the string. Okay, so what is this? Tension. So this is weight, and this is tension in the string. So here tension acts along the length of the string. So here let us consider an imaginary rectangle here. This is actually the displacement of the bob. Here mg actually, that is splits into two rectangular components. Okay, mg is splits into the two rectangular components. So this is angle theta. What about this? This one is also angle theta, because these two are corresponding angles, right? So look at this rectangle carefully. So here mg, that should be splits into two rectangular components. So mg, that is splits. mg is splits into two rectangular components. One is mg cos theta and another one is mg sin theta. What is the function of mg cos theta? What is the function of mg sin theta? That is very important. So this is perpendicular, this one is hypotenuse. What is this? Perpendicular. So this one is hypotenuse and this is base. So the base component of mg. So now mg splits into two components. So this perpendicular, hypotenuse, base component of mg, that is mg cos theta, and another one, so this is mg sin theta, right? What is this? Mg sin theta. So this is angle theta. What about this? Angle theta. So this is perpendicular. Okay, perpendicular component of mg is mg sin theta. Okay, so that is towards mg sin theta, towards the equilibrium position. Okay, so here mg splits into two rectangular components. One is mg cos theta and another one is mg sin theta. So mg cos theta balances. This point is very, very important. mg cos theta balances the tension in the string. Okay, mg cos theta balances the tension in the string, and mg sin theta acts as a restoring force. Acts as a restoring force. So mg cos theta balances the tension in the string, and mg sin theta acts as a restoring force. Okay, now let us start derivation. So by the definition of simple harmonic motion, actually here Bob execute simple harmonic motion. Okay, so the restoring force here proportional to restoring force, that is equal to minus mg sin theta. So negative sign indicates the restoring force in the string, which decreases the value of theta. So that is the significance of negative sign here. But for small angles, sin theta is approximately becomes theta. So now this equation becomes F is equal to minus mg theta. Okay, now let us consider here this distance as x. Okay, so this is a linear displacement, and this one is L. L is the length of the string. Okay, so this is L. So what is this? X. So this is angle theta. This is perpendicular. Okay, perpendicular, and this one is hypotenuse. This is perpendicular. This one is hypotenuse. So in the triangle SOA, sin theta is equal to x divided by L. Okay, sin theta is equal to x divided by L. For small angle, sin theta becomes theta. So theta value is x by L. Theta value is x by L. So F is equal to minus mg. Even for small angles, sin theta, that is approximately equal to tan theta, so that is approximately equal to theta. Okay. Actually, angular displacement is the length of the arc by radius. So your length of the arc is x, radius is L. Okay. If theta is very, very small, so arc is almost linear, straight. So theta is x by L. So call this as equation number 1. So according to Newton's second law, of motion, so F is equal to mass into acceleration of a particle execute simple harmonic motion. So F is equal to m. Alpha is minus omega square x. So here x is the displacement. So alpha is equal to minus omega square x. So this is the formula. So call this as equation number 2. Now compare these two equations 1 and 2. From equations 1 and 2, so we can conclude that so minus m omega square x is equal to minus mg x divided by L. So x, m, minus cancels here. So finally, we will get omega is equal to root g by L, but omega, that is 2 pi by t, right? So this is the next step. Omega is 2 pi by t, so 2 pi by t, so that is equal to root 2 pi by t is equal to root g by L, root g divided by L. So t is equal to 2 pi divided by, t is equal to 2 pi divided by root g by L. T is equal to 2 pi divided by root g by L, g divided by L. So finally, we will get t is equal to 2 pi, and this is shifted to numerator. So what happens? Root L by g, right? T is equal to 2 pi root L divided by g. So this is the time period of oscillation, of a simple pendulum. This is a very important mathematical expression. T is equal to 2 pi root L by G. So what about frequency? So frequency is the local of time period. So frequency is the reciprocal of time period. So F is equal to 1 by T. F is equal to 1 by T, and this is 1 divided by 2 pi root L by G. So that is shifted to the numerator. What happens? Root G by L. Okay. So this is the expression for frequency. F is equal to 1 divided by 2 pi root G by L. This is the expression for frequency of oscillation of simple pendulum. So this is time period of oscillation of simple pendulum, that is t is equal to 2 pi root L by G. So how does time period? So depends on length, that is directly proportional to square root of length, and time period is inversely proportional to square root of acceleration due to gravity. Okay, and this is very important for 5 mark. Okay, so thank you.